Welcome to part 6 of Maxwell's Verilog tutorial series. In this video, we will continue to see about the data types in Verilog. Welcome to the presentation on Verilog data types. Today, we will be covering register data type in Verilog. First, we will start with the reg data type, which is used to hold a value in a register. Next, we will discuss vectors, which allow us to declare reg or wire types with multiple bits. Then the integer data type is a general purpose register which is used to manipulate quantities such as counting and looping. Then the real data type is used to store floating point numbers. And lastly, we have the time data type used for simulation time representation. Let's talk about reg in Verilog, which is a fundamental data type used to represent registers in our designs. Registers are data storage elements in Verilog. They are used to store values that our designs will use and manipulate during simulation or operation. One key characteristic of registers is that they retain their value until another value is placed onto them. This means that once a value is assigned to a reg, it will hold that value until we explicitly change it. And the reg does not need a driver to maintain its value. It is self-sustaining in this sense. A reg type in Verilog is used to declare variables that can hold a value. This is crucial for creating state machines, counters, and other sequential logic elements. By default, a reg variable in Verilog is initialized to x. This represents an unknown state, which is useful for detecting uninitialized variables during simulation. Registers are commonly used in procedural blocks such as initial and always. These blocks are where you define the behavior of your design over time. The syntax for declaring a reg is must be down to lsb and then variable name. For example, reg data declares a single bit register variable called data. Reg 7 down to 0 bus declares an 8-bit vector register called bus. In these examples, reg data is a scalar register that can hold a single bit, and reg 7 down to 0 bus is the 8-bit wide vector register. You can declare more complex registers by specifying the range in the square brackets. In test benches, reg variables are frequently used to simulate inputs to the design and to capture the output values. In this example, we have a test bench TB with reg variables, clock, reset, and data in. We instantiate the design under test and provide initial values to these reg variables. We also generate a clock signal by toggling clock every 5 time units. The test sequence changes the reset and data in values at specific time intervals to verify the duty's behavior. In design, reg variables are used to store state information and to implement sequential logic. Here we have a simple counter module. The count variable is declared as reg because it needs to hold its value across the clock cycles. In the always block, which triggers on the positive edge of clock or reset, we check if reset is high. If it is, we set count to 0. Otherwise, we increment count by 1. This demonstrates how rich variables are essential for creating state machines and other sequential circuits. In Verilog, vectors allow you to declare nets or rich data types with multiple bit widths, which is essential for handling buses and other multi-bit signals. Here are a few examples of vector declarations. Wire 7 down to 0 bus declares an 8-bit bus. Wire 31 down to 0 bus A, bus B, bus C declares three 32-bit buses. Reg 40 down to 0 virtual address declares a 41-bit wide vector register for a virtual address. If you don't specify the bit width, the default is scalar, meaning it's just one bit. For instance, the declaration wire A creates a scalar net variable. You can declare vectors in two ways, high to low or else low to high. However, the left number in the square bracket is always the most significant bit. For example, in virtual address, bit 0 is the most significant bit. When working with vectors, you can address specific bits or parts of vectors. For instance, bus A of 7 accesses bit 7 of the vector bus A. Bus 2 down to 0 accesses the three least significant bits of the vector bus. Virtual address 0 down to 1 accesses the two most significant bits of the vector virtual address. It is important to note that you should always place the most significant bit on the left of a range specification, such as using 2 down to 0 instead of 0 down to 2. Vectors provide flexibility in handling multiple data, making them invaluable for designing and complex digital systems. Next, we will discuss the integer data type in Verilog, which is a versatile and commonly used data type for various purposes. An integer is a general-purpose register data type used for manipulating quantities. It is particularly useful for operations involving counting, looping, and arithmetic calculations. Integers are declared by using the keyword integer. This makes the code more readable and easier to understand, especially when performing operations that inherently involve numbers. While it is possible to use reg as general purpose variable, it is more convenient to declare an integer for purposes such as counting. This is because integers handle signed quantities natively. The default width for an integer is the host machine word size, which is implementation specific but at least 32 bits. This allows integers to handle a wide range of values efficiently. Registers declares as reg store values as unsigned quantities, whereas integers store values as signed quantities. This distinction is crucial for arithmetic operations, especially those involving negative numbers. The syntax for declaring an integer is straightforward: integer variable name. This simplicity makes it easier to declare and use integers in your Verilog code. For example, to declare an integer variable named count, you would write integer count and this declares count as an integer. Here we have a module named integer example. Inside this module, we declare three integer variables: count, sum, and product. In the initial block, we assign and display values to illustrate how integers can be used in Verilog. First, the count is assigned a value of 5. We display this value using the display system function. Next, the sum is assigned the result of adding 10 to count. This demonstrates a simple arithmetic operation and the result 15 is displayed. Then the product is assigned the result of multiplying count by 3. The result, which is also 15, is displayed. Finally, we assign a negative value -7 to count and to show that integers can store negative values as well. This negative value is then displayed. The key takeaway here is that while reg data type stores values as unsigned quantities, integer types store values as signed quantities, making them more suitable for operations where negative values or larger ranges are needed. To declare a real number in Verilog, we use the keyword real. It is straightforward, just like declaring other variables but with real. You can specify real numbers in decimal form like 3.14. You can also use scientific notation such as 3e6 for 3 times 10 to the power of 6. One thing to note that real numbers in Verilog cannot have a range declaration. By default, if you don't assign a value to a real number, it will be 0. When you assign a real number to an integer, Verilog automatically rounds it to the nearest integer. For example, if you assign 3.14 to an integer variable, it will store 3. The syntax is simple: real and then the variable name. Just replace the variable name with your desired variable name. In this slide, we have an example Verilog module named real underscore ex. We declare a real variable delta. In the initial block, we assign delta a value in scientific notation for E10, and then we use the $display system task to print its value. The percentage %e format specifier displays the number in scientific notation. Next, we assign delta a real value 2.13 and then print it using the percentage %f format specifier, which displays the number in floating point notation. And then we declare an integer variable I. In another initial block, we assign I the value of delta. Since delta holds the value of 2.13, assigning it to I rounds it to the nearest integer, which is 2. We print the value of I using the percentage %d format specifier, which displays it as an integer. Let's move on to how Verilog handles simulation time. This is crucial because all our simulations are based on the time progression. All simulations in Verilog are performed with respect to simulation time. It's the basic backbone of any simulation progress. Verilog has a special data type specifically for storing simulation time called a time register. The width of these time registers is at least 64 bits. This allows a very large range of time values, which is useful for long simulations. To get the current time simulation, we use the system function $time. This function retrieves the current simulation time whenever you need it. To declare a time variable, use the syntax time variable name. Replace variable name with your chosen name for the variable. Here is a quick example of how you might use a time variable in your code. In this example, we declare a variable name called saveSimTime. Inside an initial block, we assign the current simulation time to saveSimTime using $time. Have any questions or doubts? Feel free to write your comments and doubts in the comment section. Thank you. See you in the next video.